All right, the next question, a repetition from AC. Now here in an AC circuit, the instantaneous EMF and current are given by this particular expression. And you can see the phase difference between the EMF and the current is pi by 4. Current is lagging behind. And here now, in one cycle of AC, the average power consumed by the circuit and the wattless current, that is to be calculated. So let's just try to see if I calculate the average power, then the average power we know is ERMS, IRMS, cos of phi. Now be careful, you need to put the RMS one. Now this is E peak, so ERMS is going to be 100 by root 2, IRMS is going to be 20 by root 2, and cos phi, the phase difference being pi by 4, so that is going to be 1 by root 2 again. So here the value what it comes is going to be straightway 1000 divided by root 2 watt is the average power for one cycle. Although straightforward 1000 by root 2 is valid only in option number 1, so this ends up the solution, but still let's see the wattless current. The wattless current, first of all, only current means the IRMS. Sin phi is called as the wattless current because in the expression of current, the cos phi component comes in the power, so the sin phi component will not be participating in power. That is what we call as the wattless component of the current. And to calculate that value, IRMS is, yes, 20 by root 2, sin phi is again 1 by root 2, so this is going to be 10, and the power 1000 by root 2 and current 10 is in option number 1. So question number 85 has option 1 as the correct solution. Should we move to question number 86 now? Let's see. All right, question number 86 from the thermodynamics part. 2 moles of an ideal monoatomic, I'm just extracting the essential data, occupies a volume V at 300 Kelvin. The gas expands adiabatically to a volume 2V. We need to calculate the final temperature and the change in its internal energy. Okay, so let's just try to see the solution part. The solution part is going to be straightforward. TV gamma minus 1 is constant. That is how the temperature and volume are related. Now it's straightforward. T2 V2 gamma minus 1 is T1 V1 gamma minus 1, and I get the value of T2 as, right, that is going to be 300 and 1 by 2 because V2 is 2V gamma minus 1. 5 by 3 minus 1, gamma equals to 5 by 3 for monoatomic, that's a straightforward value, that's 2 by 3. Now this demands a bit of effort, like this is 4 raised to the power 1 by 3. You can just do it by hit and trial, it comes around 1.6, and when you put the value, you see the temperature comes as 189 Kelvin. I do agree that the calculation was not so abrupt, but yes, with a small bit of effort you can do. So the temperature has been calculated to be 189 Kelvin. The temperature has fallen, and this means the change in internal energy would be negative, that is straightforward. So what I will get is the change in internal energy is NCV T2 minus of T1. So here is the direct value, you will put N as 2, CV 3R by 2, right? It's monoatomic, and T2 minus T1 you can just put it, and the value is pre-calculated. This one is not so tough, minus 2.7 kilojoule would be the value. All right, so temperature final 189, the change in internal energy minus 2.7 kilojoule. So this will give option number 2 as the correct one for question number 86. So question number 86 has correct option as option number 2. Let's go to question number 87.